Hello, everybody, and welcome to Aerospike Summit 2021. My name is Micah, and I'm a cloud architect and a consultant here at Aerospike. I work with a number of our enterprise customers, helping them with their Aerospike deployments, and I also work with the Aerospike Managed Service team, where we deploy and configure and operate Aerospike clusters on behalf of our customers, and we run those in the various public cloud providers. Today I'm going to talk a bit about multi-cloud Aerospike deployments, and I'm specifically going to get into the sort of the trade-offs and the considerations in choosing a multi-cloud pattern that makes sense for an organization and the use case. So with that, let me start presenting. And to kick things off, it's important to understand why an organization is choosing a multi-cloud strategy. And in a word, it's strategy, right? Multi-cloud strategy, there it is. It's about the business strategy that's going to drive the need to go multi-cloud, and the specifics of that strategy are going to really determine what the right deployment pattern is. So, I mean, it could be to have a global footprint where some cloud providers are available in certain regions that other cloud providers aren't. So by being able to have the same applications and same database running in multi-cloud providers, you do get multiple, you get to have more geographic presence. And that's, could be even having the same data or a subset of the data replicated in all of those deployments. It's often about avoiding vendor lock, so not having all your eggs in one basket from a cloud provider standpoint. Maybe part of that is about having some negotiation power by being able to move workloads to and from various providers. There's sometimes a competitive piece to this where certain organizations are competitive with one cloud provider or the other, or maybe their key customers are competitive with a cloud provider, so they need the ability to run some workloads on certain clouds and others on other clouds. And then probably, the most common characteristic people are looking for is some means of a disaster recovery and business continuity plan around being able to recover from an entire cloud failure into another cloud. And that could be, your typical natural disaster type scenarios or cybersecurity threats or any number of scenarios organizations are looking to hedge against. So with that in mind, knowing which of those and why you're looking at multi-cloud is going to be important. If you're looking to have the ability to run multiple clouds or run in multiple clouds, or the ability to move a workload to multiple clouds, you're going to have a bit more tolerance around how you approach that, and you're going to be able to reduce cost and complexity. If your goal is more on the disaster recovery side and you're looking for a recovery point objective and or recovery time objective that's nearing zero or near zero for failure modes that are sort of cloud-wide, whole cloud, then you're going to be looking at a lot more cost complexity to get that type of architecture in place. And so that's what we're going to dive into a little bit here. So what I'm showing here are two, I would say, categories of multi-cloud deployments with Aerospike, where the deployment on the left is kind of showing a synchronous replication between two cloud providers. And what that means is we've effectively taken a single Aerospike cluster. So it's a single database, distributed database with nodes running actively in both clouds. All data that is written is synchronously replicated, and typically this type of pattern would only be used where data consistency is paramount. So this is sort of assumed that it's a strongly consistent cluster or strong consistency mode in Aerospike speak. On the right, we have a pattern which is a little different in that there's two Aerospike clusters, one running in each of the cloud providers, and data is asynchronously replicated. This fits, probably the much larger spectrum of multi-cloud strategies. It's not quite as aggressive on an RPO and RTO nearing zero, but it still can be very, very, very good to the tune of minutes. Just kind of depends on the failure mode. But it has a lot of versatility in terms of whether you're running an active passive from a multi-cloud strategy, whether you're failing over back and forth, or you're even running active-active. You're running applications in active-passive, but the database in active-active. So there's a lot of more permutations of this pattern that satisfy probably the vast majority of multi-cloud use cases. And but the first pattern we're going to look at is actually this synchronous pattern. So before I get into more of those details, I do want to emphasize this common thread that you're going to be hearing around network. Network is always a critical part of a Aerospike deployment in cloud because it has implications on cost, it has implications on latency, and those can be critical components depending on the workload. So when you add another network component or another network hop between cloud providers, you're introducing some new challenges with regards to networking. So one way or another, you're going to be leaving one cloud provider's sort of private network, which is a bit more understood and consistent and reliable, or at least its reliability is better understood. Then you're going to be going over a third network, and that could be the open internet with something like a VPN, or it could be a private network with a partner, but it's still a third component, and then into the other cloud provider. So this is just going to make network and the network design that much more critical. So with that, this will be sort of exemplified here when we look at a multi-site clustering pattern. So multi-site clustering in Aerospike simply means that the Aerospike nodes are distributed across two different sites. So this could be two different data centers is a common pattern. Two different cloud regions within the same cloud is also a common pattern. What we're showing here is that same idea, but now spread across two different clouds. So this has the nice property of a write, which is shown here, is going to be replicated to the other cloud provider synchronously, and it's going to be acknowledged back to the client so that you have that strong consistency guarantee. You're guaranteed that that write was committed to both to that node in both clouds, and therefore if you were to have to fail over or lose an entire cloud provider, you do have all of that data. Now, what should be obvious is that means that that network connection between those two cloud providers is absolutely critical. It's in the critical path for every single write. And let me show another write real quick. In this case, the master copy of this particular piece of data was on a node that was in the other cloud provider. So the application node running in GCP in this case needed to write to an Aerospike node in AWS, and then that node replicated that to an Aerospike node in GCP. So in this case, we actually had two hops across that intercloud connectivity, whereas in this case, we only had one hop. And that just, it would be about 50-50 if the replication factor were 2 and the nodes were evenly split. There's a lot of like caveats that would come into play if we were to go a level deeper, but conceptually what I'm trying to highlight here is this idea of you have a non-trivial amount of latency between the two cloud providers, and then you have different characteristics of latency depending on whether the application node is needing to write to a node in the target and then replicate back, or the other way around. So to underscore that a little bit more, like let's just to pull a number out of thin air, let's say that there was an 8 millisecond latency between these two cloud regions. So they're in the same region geographically as close as possible, but they're still different clouds. You're traversing a third-party network. What does that mean? It means that in this case, we had that 8 milliseconds latency on the replication, but the client is still waiting for that because it's synchronous. And in this case, that's now 16. We've at least doubled the latency just because this write happened to need to go to the other side. So about some portion, let's call it half in this case, of the writes are going to be twice as slow as the rest. So from an operational perspective, this creates some additional overhead in being able to know what known good steady state should look like in depending on the type of write. So you have an 8 to 16 millisecond band of known good latency, and it's going to be critical to be monitoring and alerting on cloud provider latency performance. So you're going to need to be measuring and watching for deviations for inter and intra-cloud latencies. The other sort of points I'll make about this is to talk about this network connection a little bit, right? So obviously this is critical for the functionality of the cluster, and it's in the critical path of steady state operation. Every write is going to need to traverse this network. So when you look at connecting two clouds together, the blogosphere is going to have a lot of examples about a site-to-site VPN. And indeed, that does have a lot of nice properties. All the cloud providers typically support some peering via VPN. They typically have good security protocols and high availability through BGP and redundancy and things like that. But the downside to a site-to-site VPN between two cloud providers is it's still going to be traversing the open internet. It may be secured with IPsec and IPv2 or something like that, so it's encrypted at the network layer, but it's still the open internet, and the internet is effectively a black box from a network engineering perspective. You don't know, and you can't rely on the performance characteristics of what's happening there. So that's a concern for this type of deployment. You don't want to introduce those types of unknowns in the synchronous replication if your application is mission critical. It's just asking for trouble with availability when network is having a slowdown, or it's just out, it's dropping packets, latency increased above what timeouts were set to tolerate, etc. So in this type of deployment, you really do want to look at direct connections between cloud providers. So that's leveraging a network service provider that has the direct connections between the providers and can support that connectivity. Oftentimes, this is also done with direct connections from the cloud providers to your existing network, and maybe that's your on-prem or your data centers, and that has sort of known properties to it. But for this type of workload, this deployment option, that connection, that network connection between these two cloud providers is critical. One other point I'll make on that is reads. So reads are similar in that, assuming this is a deployment option that is chosen for its properties of being strongly consistent across cloud providers, the reads would typically have that same property where some of the reads are going to be within the cloud provider, some of them are going to be from the other cloud provider. But we do have this notion of being able to relax the reads somewhat. So you can tell the Aerospike clients, which are a part of your application, that you would like for it to prefer to read from the same, what we call rack, but it's an arbitrary sort of designation. Prefer to read from that if it can, and that might be a replica. So if it is in the same cloud provider or same availability zone within that cloud provider, it'll read from that replica rather than the master copy in the other cloud. Small window of being able to get a stale read, but if that's tolerable, it can cut down on latency and cost for those reads. Now, this will get a little more complicated. I'm not depicting it here for simplicity, but there would be multiple zones in each cloud provider. And so each zone is going to be designated a rack. So it's sort of a subset of the overall number of racks. But in general, there are some things you can do to try to at least reduce some of that if you can tolerate that consistency guarantee on reads a little bit. And now we'll look at the other sort of category of deployment patterns for multi-cloud. And what we're looking at here is one cluster running in Google on the left, another cluster running in Amazon on the right, and asynchronous replication between the two. So what this means is There's basically a completely autonomous cluster in Google. It's running and replicating data. So you have a master copy and n number of replicas in other availability zones within that cloud provider. But then there's also an asynchronous replication to another autonomous cluster, and it has, its own n copies in various zones. And that is basically a complete copy of the cluster. It has all the same data, but because it's asynchronous, it might not be exactly up to date, and the application is not waiting for an acknowledgement from the destination cluster in the other cloud that it received the write. So there's a small chance of losing writes, and the destination cluster may be, somewhere in the magnitude of high hundreds of milliseconds to seconds of latency behind it. So this has some really nice properties though because of that asynchronous connectivity. One is that you can have very good performance. You're not waiting on that network between the two providers. So the applications running in Google, for example, on the left, can still be operating in that sub-millisecond to low millisecond range, just depending on some of the use case specifics. But you still get the multi-cloud where you have another copy of that entire cluster. You could even be running this active where you also have application nodes in that other cluster. And so you get you get the multi-cloud without having to take the additional cost and latency of the synchronous replication. Now, in this case, because it's asynchronous and it's using Aerospike's cross data center replication, or XDR, we do have the ability to tolerate more disruptions in the network. So if the network slows down a little bit and replication slows down from, a few hundred milliseconds to a few seconds and then can catch up, that is tolerable without impacting the applications. The applications are still just dependent on the nodes within that cloud provider. So that's going to be much more tolerant of that site-to-site VPN, which is over the open internet. It still might alert if you're slowing down and backing up, but it wouldn't break the applications. Likewise, if you have a network service provider in play, but you still might experience network disruptions, dropped packets, increased latency for short periods of time, things like that. This is a good pattern for that. Now, of course, what that means, however, from a disaster recovery standpoint, is that if you were to lose an entire cloud provider, you might not have gotten all of the writes all the way to the other side, and so your RPO, your recovery point objective, might have to be tolerant of not being near zero and instead being in the order of seconds to minutes or whatever that disruption was. So if you can tolerate that from a DR standpoint, but you do want to still have, and you still want to have multi-cloud where both clouds are active, they're ready to go, and a recovery time would be near zero. This is a very good deployment pattern for that. Similar to what we saw in the other pattern, you can also do the reads from the master or the relaxed read from a replica, and in this case it's all contained within the cloud, so it really does just fit our typical cloud deployment pattern. So this would be application nodes reading the replica from the zone that they're in and preferring that over always crossing zone and reading from the master. So this also has a benefit of being able to get a lower cost for steady state application use, where as much as possible they're not even leaving the zone, let alone leaving the region or the cloud provider and traversing the third-party network. And so finally, just to kind of summarize that up, I'll wrap here. The multi-site clustering approach to a multi-cloud strategy with Aerospike is really something that has its niche in mission critical data. The data consistency and that consistency guarantee is paramount. It's more important than latency. It's more important than costs and performance. It really is about having active, strongly consistent data, and the goal being to have RPO and RTO in the event of a disaster where the failure mode is a full cloud failure. near zero because there's an entire accurate copy of the data in the other cloud, which is active and operational. The other approach that we looked at is using cross data center. This is the asynchronous replication. This is the pattern that fits pretty much everything else, where mission critical performance and availability are key requirements. The RPO and the RTO can tolerate something above zero. It can still be very good, but there is possible data loss that would occur if you were to lose an entire cloud provider suddenly. It does support active-active and active-passive multi-cloud topologies. It's very versatile. You can kind of mix and match various Aerospike features and deployment patterns based on what you're trying to achieve. And because of that, you can tune this to better fit budgetary constraints if the trade-offs make sense for the use case. So that would be, I think the 10,000 foot view of some multi-cloud options in Aerospike. This is certainly a more advanced topic, so I highly encourage you, if you're thinking about multi-cloud or you just want to learn more, come talk to us. Our support and services team can help work you through the types of decisions and trade-offs that you're going to want to make and help figure out what the right Aerospike topology and configuration would be to have a multi-site deployment. And again, I covered kind of two common and I think what would be interesting use cases or deployment patterns here. There are some that are even more pragmatic if you don't need mission critical systems at all even, and so sort of more of an active passive standby type deployment and things like that. So there's more things to explore with multi-cloud deployments in Aerospike if you're interested, but this is the gist, and I hope that was helpful. I will kill my presentation now and we can do some questions. Thank you everybody for listening.